Hello everyone, welcome to my video. Today we will be solving another geometry problem from the International Mathematics Competition 2010. We have here a circle and two semicircles inscribed in a square. They have a radius of 1 cm each. Now, the goal is to find the area of the square. Okay, so there are actually key observations here that we can use to solve the problem. One is that if we connect the centers of the circle and the two semicircles, we actually form an equilateral triangle. Okay, so let's do that. So let's locate first the centers and then connect to form an equilateral triangle. Okay, another observation is that the the square or even the entire figure, including the circle and the two semicircles, is symmetric about the diagonal AC. So why not also draw the diagonal? So let's do that. Uh, okay. Now these observations are useful because these reveal some other information in the figure. We can actually extract some other values from here. Uh, for example, because the square is symmetric about the diagonal AC, this one here is actually 90 degrees. Okay, so the green segment is perpendicular to the blue segment. Another is that the diagonal divides angle C into two congruent angles. So this one here is 45 degrees. This one here is also 45 degrees. Okay. Let's label also the radius. So this is 1, 1, 1, 1, and 1. Okay. Now going back to the angles here in this triangle, take note that we have here 45 degrees. This is 90. So automatically this is also 45 degrees. And so this is just an isosceles triangle, right? Isosceles right triangle. So this side here must also be 1 centimeter. Okay. Now, it seems that it's possible for us to find the length of AC. Okay. And also, if we actually find AC and relate it to the side of the square, we can actually get the area of the square. For example, if we represent, or in particular, if we represent the side of the square by, let's say, S, this one also by S, take note that the area is just S times S, or S squared, right? So area is just equal to S times S, or S squared. And also, by the Pythagorean theorem, S squared plus S squared is equal to AC squared, right? Or 2S squared equals AC squared. So if we divide both sides by 2, we have S squared equals AC squared divided by 2. So if we know AC, we can easily find the area of the square, which is S squared, right? Okay, so it seems that we are on the right track. So let's continue finding some other parts of the diagonal. Okay, so let's focus now on the equilateral triangle and find um, the altitude of the equilateral triangle. So let's label that one by, let's say, y. Okay, so y now is, or y can be determined by using the Pythagorean theorem. So let's do that. We have y squared plus 1 squared equals 2 squared, or y squared equals 4 minus 1, which is equal to 3. So y is now equal to square root of 3. Okay, so we still have another part of the diagonal that we need to find. Okay, it's in the lower left portion of the square, right? So let's label that one by x. Okay, let's say this is x. Now, how do we find this length? Let's draw another radius from this center perpendicular to the base of the square. Another radius perpendicular to the vertical side of the square. Now recall that the radius is just 1 unit, right? So if this is 1, take note this is a square. We form another square, right? So this one here, it must also be 1. This one is the radius, so this is 1. So we can easily see that x squared is equal to 1 squared plus 1 squared by the Pythagorean theorem. So this is equal to 2. And so x is equal to square root of 2. Okay, so now we know what's AC, or the length of AC, right? So AC AC is equal to square root of 2 plus the square root of 3 plus 1. Now if we go back to this equation here on top, we can just substitute the value of AC to get s squared, which is the area of the square. Okay, so let's do that. S squared is equal to the square of the square root of 2 plus the square root of 3 plus 1, and then divided by 2. Okay, so in expanding the numerator, you can use the FOIL method, but I will not do that. I'll just apply an identity that will make the expansion easier. So I don't know if you're familiar with this identity, but the square of a trinomial a plus b plus c is equal to a squared plus b squared plus c squared plus 2 times ab plus bc plus ac. Okay, so this identity will save us some of the work. Okay, so if we take a as square root of 2, b square root of 3, and c 1, we can just have square root of 2, square root of 3 squared, 1 squared, and then 2 times a times b. A times b is square root of 2 times square root of 3 plus bc, square root of 3 times 1, ac, square root of 2 times 1. Okay, so we can just easily simplify that, and this one is 2, this one is 3, this one is 1, right? So that's 6. And then this one, square root of 2 times square root of 3, that's square root of 6 times 2, 2 square root of 6. Square root of 3 times 1, square root of 3 times 2, 2 square root of 3. And finally, we have square root of 2 times 1, that's square root of 2 times 2, 2 square root of 2. And so, the numerator is just 6 plus 2 square root of 6 plus 2 square root of 3 plus 2 square root of 2 divided by 2. And we can actually cancel some common factors. So s squared becomes 3 plus square root of 6 plus square root of 3 plus square root of 2. Okay, so we can rearrange this to look better. For this to look better, so we can actually have square root of 2, but it's not really necessary. So this is square root of 2 plus square root of 3 plus square root of 6 and then plus 3. Okay, so this is now the area of the square in cm squared.